Today we are going to start talking about arithmetic and composition of functions. So as usual, I will give you a brief perspective of what this topic is going to look for us. So when we talk about arithmetic of functions, we are basically concerned about how to add, subtract, multiply, or divide multiple functions when their domain allows us to do so. So to say, if you are given with two functions, fx and gx, and you know that domain of f is given by, so I'm going to write it this way, domain of f is say d sub f, and similarly domain of g is given by d sub g. And d sub f and d sub g are sets. So for us, they are intervals or set of real numbers on the number line. Anyhow, if we are having two functions fx and gx and we know their domains, then I can associate these two functions by adding them, subtracting them, multiplying them, or dividing one by the other. As I said, we have to be careful how much the domain of these two functions lets us do these things. For example, if you are trying to add two functions a plus g, then by definition we will be able to say that look at your function fx, then look at your function gx, and add them, and you get the function a plus g. With the restricted domain, so domain of this a plus g function, the new function that we have created, is going to be the overlap of the domain of the function f and the domain of the function g. Similarly, if I have two functions f and g and I'm willing to subtract g from f, then the definition of function subtraction will tell you looking at your function fx and then subtracting the function gx and then combining like terms. As usual, the domain of this function is going to look like the overlap of the domain of the function f and the domain of the function g. So I will say domain f minus g is overlap of domain of f and domain of g. And I can do the other two operation, algebraic operation, multiplying two functions. I will say if I multiply two functions, then that looks like multiplication of the explicit form of the function fx with the explicit form of the function gx. And as usual, you can imagine by now, domain of f times g, the product function, is also the overlap of f and g's domain. Finally, we will be thinking about division of two functions. Say I'm dividing the function f by the function g. Then this is as simple as writing the function fx in the numerator and writing the function gx in the denominator and do possible division. Domain of the division function is a little different than the previous three. So domain of f over g is not only the overlap. So first of all, I'm going to take the overlap of the domains for f and domains for g, but not only that, except any point where the bottom function, in our case it is g, is equal to 0. Why? Because again, remember, as we have seen rational function, if the denominator is equal to 0, the function becomes undefined. So we want to make sure we are not going to take any real numbers for which the function on the bottom, which is gx in our case, is not equal to 0. In order to make sure that gx is not equal to 0, we first enforce gx to be equal to 0 and then discard all the points. So we will start working on some of these problems, and then we will start talking about the other way of combining functions. So these are just basic definitions that we have talked about, and now we are going to directly go and start working with our example 1. As you can see, it is asking you to find f plus g, f minus g, f times g, and f over g, and then asking you to find the domain of each of this combination of functions. So let's start with the problem number A. First, we're going to start writing f plus g of x. As per definition, this is fx plus gx. So what is fx plus gx? You look at your fx, that's 2x plus 3. You look at your gx, that's simply x minus 1, and then you combine them. So what I get 2x plus x, which is 3x, 3 minus 1, which is plus 2. So that's your new function f plus g. And you're done. Your f plus g of x is 3x plus 2. Let's talk about the domain. So we'll look at our function f. See, f is a linear function. And as we know, linear function, the domain is everything. So it is negative infinity to infinity. G is a linear function as well. So the domain is pretty nice. It's still negative infinity to infinity. Now we will think about the overlap of the domains of f and g. And we're going to do this work only once, as this is going to be repeated as the domain of f minus g and f times g. So overlap of domains of f and g. Draw a number line. This time your work is pretty simple. Your domain for f is everything. There is nothing that we need to discard. So say this is the domain of f. And then I will use a different color in order to understand what is the domain of g. G being a linear function, the domain is also everything. And see, so on the entire real number line R, if you consider this as the real number line R, on the entire real number line, both function has their domains. That means the overlap of these two domains is the entire real number line. In other words, domain of f plus g, which was my required answer to be found out, is going to be the entire real number line, which I know in interval notation is negative infinity to infinity. Once I have done this work for f plus g, I can repeat answering the other questions, and I don't have to do this number line work anymore for f minus g, f times g, and so to say for f over g. Let's try to find out f minus g now. So f minus g is again a combination of two functions, and it is defined as the explicit definition of fx minus the explicit definition of gx. And as I can recall, your fx is equal to 2x plus 3. Because you are subtracting now, I would say put your gx, the entire explicit form, inside parentheses so that we don't forget to distribute the minus sign. Remember, your gx was x minus 1. So I will do one more line and write it as 2x plus 3. Then start distributing the minus, so minus x. Minus times minus is a plus, so plus 1. So I get 2x minus x, which is a positive x, 3 plus 1, which is positive 4. So that's your f minus gx. Don't forget to write down the domain of this thing. I don't have to do the work anymore, but I will say domain of the function f minus g is negative infinity to positive infinity again. Then your next objective is to find out the product of the functions f times g, which is f of x. So write explicitly what f of x looks like, and then write explicitly what g of x looks like, and then multiply. So f of x is 2x plus 3. G of x is x minus 1. As you can imagine, I'm going to FOIL, which we will do by distribution. So first I can start distributing 2x over x, and I get 2x squared. Then I do 2x minus times minus 1, which is minus 2x. Distribute 3, you get plus 3x. Distribute 3 over negative 1, you get negative 3. So you get 2x squared plus x and negative 3 as the product of these two functions. And finally, I'm going to wrap it up by writing the domain of f times g. So we'll go ahead and say that domain of the function fg is negative infinity to positive infinity. F over g is rather easier when I'm talking about the algebraic explicit form of the division of the two functions. So this is writing fx in the numerator over gx in the denominator. I know that fx is 2x plus 3 and gx is x minus 1. Since I have two linear factors on top and bottom which are not like factors, there is no cancellation. Hence, this is your final answer for the algebraic form. Now we will think about the domain. Remember, this time I need to do a little extra. I know the overlap of the domain is everything. But then I know x minus 1 should not be equal to 0. So let's force x minus 1 to be equal to 0. And I would know x equal to 1 is the bad point. So whatever the overlap was for the last three exercises, discard the point 1 from it. So this is your 1, which is a bad point. Don't take it, take everything else. And hence we get to say the domain of the division of the two functions f over g is negative infinity to positive 1 and then positive 1 to positive infinity. That would answer your question in entirety. We'll practice one more of this kind, and this time again we will have two different functions given to us, and what we would like to do is for these two functions combine them as we have done it, exercise A. So first we're going to start working with a plus g. A plus g of x by definition is going to be f of x plus g of x. So let's write it one time, f of x plus g of x, which is equal to square root of x plus x minus 4. And see, none of these terms are like terms. So we will not try to subtract or add or combine any terms, and we will just call this one is my final answer. Domain. So again, I will get my number line and we'll first try to do the domain of fx. We have to be careful for the domain of fx. Fx is square root of x. And I know there is a restriction. X must be non-negative. What does that mean in mathematical notation? That is, x must be greater than or equal to 0 as we are trying to take the square root of x and get real outputs. So if it is my number line and 0 is this point, then I'm supposed to take anything on the right hand side of 0 as x can be greater than 0, and I can include the point 0 as well because of the equality. So domain of f in interval notation is 0, infinity. Because of the equality at 0, I can use the close bracket, and infinity is always open. So let's first get that done. So this is 0, and I can take anything starting at 0 and go to infinity as the domain of f. I still need to do the overlap. So now I look at the function gx, which is x minus 4, and remember that's a linear function. These are the nicer function. The domain is everything or all real numbers or negative infinity to infinity. So I will use a different color to write the domain of g, and then I will try to see on the number line where are the two colors overlapping. And if you see carefully, the overlap happens starting at 0 going all the way to positive infinity, including the point 0. So it's precisely the domain of f, which I'm going to go ahead and say, I will say overlap of the two domains for f and g is close interval 0 and infinity. Hence, this is the domain for f plus g. And again, recall, I just have to do this work once. Once I have done it for f plus g, I don't have to repeat this work for f minus g, f times g, or f over g. So domain of f plus g is close interval 0, all the way to positive infinity. Let's work with f minus g, the algebraic form now. F minus g of x, by definition, is f of x minus g of x. F of x is square root of x minus, again, remember what I told you. When you are subtracting a function, put that entire function first inside parentheses so that you don't forget to distribute. Your gx is x minus 4. So you get square root of x minus x plus 4 after the distribution. And that's your final answer because there is no like term that I can combine. I will leave my answer there. Domain. Domain of f minus g is still the same as the domain of f plus g. So I go ahead and say that this is 0 to infinity. F times g. F times g of x. Well, you are going to write square root of x for fx. Actually, let me write down the definition so that it reminds us every single time what we are trying to do. So it is fx times gx, and recall fx is square root of x, and x minus 4 is your gx. Now, if you want, you can actually go ahead and simplify this term as x times square root of x minus 4 times square root of x, which in my mind is no better than whatever we had in the previous line. So if someone wants, they can end the problem right here and I will give them full credit. I don't actually have to distribute because it doesn't make the function look any better. So the final thing is writing the domain of this function. So the domain of this function, f times g, is still positive, closed 0 to positive infinity. F over g. By definition, f over g is the function fx in the numerator and the function gx in the denominator. So I get square root of x on the top, x minus 4 on the bottom. And there is no like factors on top and bottom, so there is no cancellation. But what you can now do, you can now tell yourself that once I have this information, I'm going to simply draw a number line, think about the bad points for the bottom, and hence get the domain. So first and foremost, remember the existing overlap for f and g's domain was 0 to infinity. So this is the overlap. Do not forget that. I have that. And you're going to discard the points that makes the denominator function equal to 0. So I set x minus 4 equal to 0. Hence x is equal to 4. And that's your bad point. You don't want this. So put x equal to 4 and put an open hole there. So what it does mean for us that I will take everything till I reach the point 4 starting at 0. Then I stop. I don't take 4 and then I start again at 4 and go ahead and take everything that are more than 4 or greater than 4. Hence the domain of f over g is closed 0 to open 4 union open 4 to positive infinity. Answers my question. And this is very basic. As you can imagine, the calculations are not at all difficult for these problems. As long as we are careful about distributing minuses properly, this problem should be pretty simple. I will wrap it up by doing one word problem, a real life application problem. So let's go to page number 2. Example 2 is telling us the bar graph shows the numbers of births and deaths in a country for 6 selected years. The functions bx and dx shown below respectively model the number of births and deaths in thousands, where x is the number of years after 2000. So the function bx, as you can see it here, 7.5x squared minus 14x plus 4044, represent the number of births x years after 2000. So for example, if I'm using 2003, then x is equal to 3, as 2003 is 3 years after 2000. So if I put x equal to 3, the number that I get from the function bx is going to represent the number of births in this country in the year 2003. Similarly, you can interpret dx. Dx is the number of deaths in the country X years after 2000. So the first question is asking us, write a function that models the change in the country's population for each year from 2000 to 2005. So recall change of population. If I want to give it a variable name, and I can use any letter for doing this thing, but because of the word population, it seems natural for me to say change of population px is bx minus dx. Let's try to think about this thing for 1 minute. Why I said change of population will be bx minus dx. Think about how the country's population is changing. Say, for example, this compartment is representing the country's existing population. The people that are being born is going to be extra input to the existing population, and then unfortunately some people that are dying is going to be, and what are the reducing factors in the existing population? Well, the people that are dying. So if I can find the difference between the number of births and number of deaths, that will be the change in the existing population. So I will say the change of population is a function which is the difference between the number of births and the number of deaths. Now remember, we have explicit form for both number of births and number of deaths in terms of functions. These are bx and dx. So I'm going to just write them down as we have done in composition of functions. So 7.5x squared minus 14x plus 4044 is the number of births. Now I'm subtracting, so I want you to remember again, you put the entire function dx inside parentheses. And that is going to be minus 3.5x squared plus 19x plus 2409. So let's simplify this quantity, which will give us the explicit form for the change in population of the country. So it's 7.5x squared minus 14x plus 4044, and then you start distributing. So see, minus times minus will give you a plus 3.5x squared, then minus 19x, and finally it will give you a minus 2409. So we'll combine the like terms. 7.5 and 3.5 together is 11x squared, minus 14 minus 19 together is minus 33x squared. I'm sorry, x. And then plus 4044 minus 2409. So 14 minus 9 will give me 5. 3 minus 0 is 3. And then 10 minus 4 is 6. 3 minus 2 is 1. So plus 1635. So that's your final answer. This is the change in population in the explicit form as a function. 11x squared minus 33x plus 1635. The second question is going to give us some interesting data. Use the function from part A to find the change in the country's population in 2003. First, understand what is in 2003. In 2003, since 2003 is 2003 minus 2000, many years after the year 2000. It talks about the x. X is equal to 3, because this is how many years 2003 has come after 2000. So x in 2003 is x equal to 3. So how do I understand the change in population in 2003, which is our required answer in this question, change in the country's population in 2003? I'm going to input 3 as x in the change in population function. So that will give us P of 3, which you know how to evaluate. You're going to say this is 11 times 3 squared minus 33 times 3 plus 1635. So this is 11 times 9 minus 33 times 3 is 99 plus 1635. 11 times 9 is 99 as well, minus 99 plus 1635. As I can see, the calculation is not at all difficult in this one. It's 1635. Then don't forget about the unit. What do I mean by that? See, all these functions, when you calculate them, they are in thousands. So it is 1635 thousands many people, representing the change in population for the country in 2003. So that will be your full answer. In 2003, the change in population will be 1635,000 people. Does this result in part B overestimate or underestimate the actual population change in 2003 shown by the bar graph? By how much? So actual population change, and these are going to be data that are going to come from the bar graph. So let's go ahead and look at our bar graphs. So if you look at the colors, it is clearly describing which year what is the number of births and number of deaths. Number of births are in red, number of deaths are in yellow. So in 2003, number of birth is given by 4090, number of death is given by 2448. So 4090 is your BX, and these are the actual number. DX is 2448, and also these are all in thousands. So let's do this calculation. 10 minus 8 is 2, 8 minus 4 is 4, 10 minus 4 is 6, and 3 minus 2 is 1. So 1642 thousands. And now my final question is asking me, you estimated this number in 2003, and you found in 2003 the actual population change. So your estimation is over or under? See, your estimation is 1635. So this is smaller than the actual population 1642. So you underestimated. So we'll say we did an underestimation. And then the question is asking you by how much? By 1642, that's the actual data, minus 1635, this is the estimated data, thousands. So how much was the underestimation? The underestimation was done by 7 thousandths. And I actually use 7,000, so you don't have to write it anymore. 1642 minus 1635 is 7, so I will go that the underestimation was by 7,000 people. So this is one way of combining functions. In our next 3 pages of lecture note, we're going to talk about a different way of combining functions, which is going to be extremely crucial for us to learn for the rest of the semester. And this is going to be called composition of functions. So again, I'm going to brief composition of function a little bit before we start working on problems. Recall, if you are given two functions fx and gx in such a way that the domain of gx is a subset of the domain I should have said the range of fx, then the composition of f and g is denoted by f. I use this small circle and I'm going to call it compose G, and is defined by I am making a couple of mistakes here. It should have been said G composed f, and I will explain that in a second, and is defined by executing the function f first on the domain of fx, then executing the function g on the range of fx. So this is the formal definition of a composition. Let's try to understand in our application terms. How would we use the definition of composition of two functions to understand functions better in our class? Well, think about a function f first. So this is the domain of the function f. So what f is doing, it is taking input from this domain and giving you output in this range for the function f. For example, say this is x. You are using this rule f and you are getting a new output, a new height, a new value, f of x. Then what I said domain of the function gx is a subset of the range of the function fx. What does that mean? It means if this black circle is the range of f and you think of a smaller circle inside this black circle and call this circle the domain of the function g. First, I need to be in this situation. Then this point fx, which was output for f, is now input for g. So I can apply g on this point and go to the range of the function g and get a new output. And what I call this output? I call this output g applied on the output of f for the input x, or g composed f of x. So as you can imagine, it depends which function I have done first and which function I have done afterwards. For our example, we have done f first and g second. In this situation, we call f the inside function and we call g the outside function. And you can associate the terms inside outside in how we write g composed f of x. See, f is inside, so f is called the inside function, which is the first function to be executed, and g is outside, which is the second function to be executed. So if someone tells you that you want to find g composed f for a function, you will say f is first, or the inside function, g is second, or the outside function, and will be defined by do f first over the input x. You get the output, treat this output as your new input, and apply g on that output. As you can now imagine, if our domains for f and g permits, then I can switch their order. And it is very important that you understand that domain is going to permit to switch the order of f and g. In this situation, the role of f and g has been reversed. F is now your outside function, or the second function to be executed, and g is your first function to be executed, or the inside function. Again, I want to precisely remind you, this is only going to be possible if the domain of f and g and the range of f and g are permitting you to do so. And I will define this situation by writing f outside and g inside. And what do I want to understand about the domain and range of this function? Since g is the function you are executing first this time, you will start with the domain of g, and you would like to see what is the range of the function g. So say this is the range of the function g. you take an input x and you give the output of gx, you want to make sure that this output gx is inside the domain of f. Or in other words, the domain of f, you want to make sure is going to be lying inside the range of g. So this is your domain of f. You want to make sure domain of f is inside, is contained. That's why I put that C other way around. Domain of f is contained in range of g. Contained in range of g. I can go ahead and make it more precise. Domain of f contained in range of g. As soon as I have ensured that, then I get to say that, well, since g of x, the output, is inside the domain of f, I can treat this output as the input of f. And then I can do the function f to go to the range of f and call this new output f of g of x. So these are the formal approaches of understanding what is the composition of two functions. In our college algebra class, we would like to use these ideas and apply them in executing function compositions and decompositions. So let's go to our problems and try to understand and execute these processes. So I have described the process of composition, and we're going to start working with example number 3. This one is giving you a function fx equal to square root of x and gx equal to x minus 1, asking you to find the composition of f with g, g with f, and then finally evaluate the composition f with g at the input 2. And see, it is not actually talking about the domain, so for this problem, we will not be concerned about finding the domain of this function. So first, let's think f compose g of x. This is the composition of two functions. As soon as I have written it this way, you would know that this is the first one to be executed. This is the second one to be executed. What does that mean? It means you will write down f as it is. For the input of f, you will put the first function, which is gx. Then change this input, gx, by the given explicit form for gx, so x minus 1. Finally, look at your fx. The explicit definition of fx is square root of x. So I say square root in place of x. This is my input, which I'm going to put here and say this is square root of x minus 1. And I have done the explicit composition rule for f compose g. And that's my answer, square root of x minus 1. So let's do the other way around. G composed f of x. So this is going to be g of f of x. Same thing. This time f is your inside or the first to be executed. So keep g and write down the explicit definition for g f, that is square root of x. So I'm changing fx by the definition of fx, which is square root of x. Then look at your explicit definition for gx. This is x minus 1, but input is square root of x. So put that in place of x and you get square root of x minus 1. And that answers your question. And think about square root of x minus 1 as a quantity and square root of x minus 1 as a quantity are not necessarily equal to each other. Why? Well, we can try answering questions and also at the same time try to understand why these two things are not equal to each other. So let's find out f compose g of 2. How do I find f compose g of 2? I look at the explicit definition for f compose g of x. Think about that. That's square root of x minus 1. So you get square root of 2 minus 1 because you are replacing x by 2. So I get square root of 1, which is 1. But how about now I want to know g composed f of 2. Well, think about the explicit definition of g composed f of x. It is square root of x minus 1. So replace the x by 2. You get square root of 2 minus 1. And remember, square root of 2 is not 2. So if I am interested in knowing how much is square root of 2, then I will see, I can find it from the calculator. So let's try to get that from the calculator real quick. So square root of 2 is 1.414. So what does that mean? It means 1.414 minus 1 is going to be g composed f of 2. So I will say 1.414 minus 1, which is 0.414. Clearly, as you can see, these two things are not equal. And that tells me it matters whether I treat f as the first function to become computed or g as the first function to be computed. The answers are going to change. Let's practice a little more. This time your fx is square root of x squared plus 3 and gx is x squared plus 8, and I'm going to do all three steps as we have done previously. So first we're going to do f compose g, and I know g is the first function, so I will say f and put g of x as the input of f. What is g of x? G of x is x squared plus 8. Now I look at my f of x. F of x is the square root function and it is x squared, but this is my input, so I replace x by this input, x squared plus 8. Then I square it. Remember, it was x squared. In place of x, I have put the new input and then I squared it. 3 doesn't depend on the input, so I don't change it. I just say plus 3. Let's simplify the inside. By simplification, I mean FOIL. So x squared plus 8 whole square is x squared plus 8 times x squared plus 8. And then I have plus 3 separately. So I will start distributing. I will get x to the power 4 plus 8x squared plus 8x squared plus 24, which is equal to square root of x to the power 4 plus 16x squared plus 24. And that should be my final answer for the composition of G with F when I do G first. I'm sorry. So let's now think about G composed F. You know, when I write G composed F, F is the first one to be executed. So I will say it's G with the input of f of x. Now think about f of x. F of x is square root of x squared plus 3. So that's the new input for your function g. I just replaced f of x by square root of x plus 3. Well, what is g of x? G of x is x squared plus 8. So instead of writing this x, I will write this input, which is square root of x squared plus 3. That's the input. This is your new x. Remember, now you are supposed to square it. So square it and then 8. And then you are simplifying. But this is nice because square and square root should cancel each other. And I should get x squared plus 3, the inside input for the square root. And then you have the separate 8, which is pretty simple to manage. And that's going to be x squared plus 11. So clearly you can imagine this function is not equal to this function, and I'm going to show you by evaluating both composition at the point 2. For example, f compose g of 2, when I'm understanding this thing, I'm replacing f compose g of x, the x in that expression, which is this one is your f compose g of x, replace x by 2, you get 2 to the power 4 plus 16 times 2 squared plus 24. 2 to the power 4 is 16 plus 16 times 4 plus 24 should give me 16 plus 64 plus 24. And when I simplify that, I should get, say, 16 plus 64 is going to be 80 plus 24 is going to be 104. And I don't have to simplify that any further because square root of 104 is not a perfect square. What else? In order to see that f composed g and g composed f are not the same thing, I can find g composed f of 2. Well, what will be g composed f of 2? it will be 2 square plus 11 because I replaced in G composed f of x the x by 2. So for x equal to 2, I will square it. I will get 4 plus 11, which is a square root of 15. Clearly, square root of 15 is not equal to square root of 104. So the composition might not be the same when I switch the order of execution of the functions f and g. These processes are called composing two function. We'll do one more exercise of this type and then we will think about decomposition of a given composition. So this one is interesting because it has three functions, f compose g compose h, and I want to know how much is it at 6. The process doesn't change. Think about f compose g compose h of x as inside outside. This is the first one to be executed. G is the second one to be executed. And f is the third one to be executed. So how do I write it? I can write the outside most, and then I can write the inside input, and then I can write the inside most input, which is h of x. First, I replace h of x by the formal definition of h of x. So I go ahead and say that this is equal to f of g of, and think about h of x. H of x is 2x cubed. So I'll go ahead and say that this is 2x cubed. Now I will execute what g is going to be. So I will say this is f of, I said we will execute g. Look at g, g is 1 over 2x. So I can go ahead and say that in place of writing g of 2x cubed, it is 1 over 2. I will pause. Instead of writing x, I will write the input, which is 2x cubed. So times 2x cubed. Let's simplify it. The inside first. So this is equal to f of 1 over 2 times 2 is 4, x cubed. Finally, I try to find what is f of x. F of x is 8x squared plus 2. So I do the same thing. I say it is equal to 8. I pause. In place of x, I write down whatever I have seen as the input, which is 1 over 4x cubed squared plus 2. And then the rest is simplification. Remember, you have a fraction, so square the top, square the bottom. So you get 8 times 1 squared is still 1. 4 squared is 16. X to the power 3 squared is x to the power 6. I simply multiplied the two powers. Plus 2. Now see, I can divide 8 and 16 both by 8. I will get 1 on top, 2 on bottom. 1 times 1 on the top is 1, and the bottom is simply 2x to the power 6 plus 2. So I have simplified the composition of three functions, f, g, and h. To get my answer, I want to evaluate this function at 6. So I will go ahead and say that this is equal to f composed g composed h of 6. Look at your explicit form of the function and replace the x by 6. So you get 1 over 2 times x is 6 to the power 6 plus 2. Remember, this 6 is, the power 6 is coming from the function, and the 6 as the input is coming from the input in the question. So possibly I will just execute how much is 6 to the power 6, and that should be done in a calculator. So let's try to do that. 6, and you are raising 6 to the power 6, so you get this number, then you times it by 2, and that should be the bottom, which is 93,312. So I go ahead and say that 1 over 93,312 plus 2 is the final answer for the composition. If you want, you can find the common denominator and combine these two, but I would say that we're good at this point and we can leave my answer this way. So that kind of wraps up talking about composition. The next set of examples, I will give you the composition as in f compose g, and you want to decompose them separately for the functions f and g. So the question is saying, if h is the composition of two functions f and g, so hx is f compose g, then identify what is f and what is g. And how do I do it? Think about what will be g in this one. That's the inside one. And f is the outside one. So you're trying to find out what is the inside and what is the outside in this composition. Inside is pretty simple, 3x minus 1. That's inside. So you're going to say g of x is equal to 3x minus 1. How do I understand the outside? Outside function is fx. What you have done to the inside? You have done inside to the power 4. Look at your f of x. The inside is x. So now, using this pattern, I will say whatever is in inside, which is x, to the power 4 is the outside function. So the outside function is x to the power 4. Answers to your question. You have decomposed the composition h equal to f compose g in terms of g and f. Let's try it one more time. Again, hx is f compose g of x. That's given in the problem, which I can write as f of g of x, and think about inside outside. This is the inside, f is the outside. So now it is twofold. Identify the inside, which is the easier one. It's 2x minus 5. And what you have done to the inside? You had the inside, you just wrapped it in the absolute value. That is going to help you understand the outside function. In the outside function, the inside is x. Wrap it around inside the absolute value, and you got your outside function. And that answers your decomposition question. Similar example in the third one, we have hx equal to x minus 9 squared. It has been told to us that it is f compose g, so g is inside and f is outside. I have, for simplicity, given you what is f of x. F of x is x squared. You just find me the inside function gx. Well, that's very simple. Look at the inside. It's x minus 9, so gx is x minus 9. And we are done. Let's do one example of composition from the graph. So I have two graphs. The blue one is the function fx, and the red one is the function gx. How do I do it? First and foremost, you write your function, the composition, as g of f of negative 2, because f of negative 2 is the inside input for the function g. What is f of negative 2? Since the input is negative 2, that's your x. So let's go to x equal to negative 2. That's there. And find how much is the height of the blue function, the f function, at this input. So I have to go touch the graph, and this is the height. And if you think about this, this is the 0.7. So f of negative 2, that represents the height of the function f at the point negative 2, at the input negative 2, is 7. So how do I write this question now? I write it as g of 7, because those two things are equal to each other. Now see, 7 is your input, but this is the input for the red function or the g function. So let's go to x equal to 7. Try to find where at this point you can meet the red function. This is at this height, which is negative 9. So the output for g at the input 7 is equal to negative 9. So what did I answer? I have answered the question. G composed f of negative 2 is equal to negative 9. This is what all we wanted to talk about composition of function. In our next class, we're going to extend it a little bit and would like to understand the concept of inverse functions so that we can start studying exponential and logarithmic function. I will wrap our class today. If you have any question, please email me and I will get back to you as soon as I can.